before we start the meeting, please change from your side. Otherwise, if we see that any participants who has not got registered and somebody who is outsider by name, as it is identified in our list of participant box, we will be forced to remove those participants. Shogato is there. Shogato is keeping track, and many other Prosenjit is there who is also keeping track. So please do this needful as soon as possible.
And another thing is that you will be provided certificates after attending the program. If you don't write your name properly, so we cannot provide you certificate.
Exactly.
Okay, sir, excuse me.
Yes.
How to rename ourselves? I don't know the method. Can you please tell me?
I think you have to log out, and then you can log
exactly.
in.
Exactly.
YouTube গিয়ে rename করে দিলেও হয়ে যায়.
That is also possible.
Abhijit?
Yes.
I think we can start now, isn't it?
Yes, Maitridi is in. Now we can see Maitridi. আপনার ক্যামেরা এবারে কাজ করছে।
আমি already start করলাম, ক্যামেরা is পুরো
আচ্ছা, তাহলে ওটা মেবি অন্য কোথাও একটা লগইন হয়েছিল।
হ্যাঁ, exactly.
Can you start now? Is there any more students in the queue who are going to join?
157 right now.
Yeah.
But it's 10টা 8 হয়েছে, so I think if you want you can.
Okay, Maitridi, can you start now?
Sure.
Okay. So, good morning, everybody. Welcome you to JBNSTS our webinar. This webinar will be presented by Dr. Jbwebinarjr. He is already there. And you know, in this current pandemic situation, we are organizing several webinars for you to understand, to get some information about the various fields of science and technology. And this time we are organizing a webinar regarding X-ray crystallography and its application to various interdisciplinary fields. So we welcome you all. And in this perspective, I would like to request our director to give the welcome address and introduce our today's speaker, Dr. Jbwebinarjr. Please.
Yes. Good morning. Good morning to all of us, but good evening to Dr. Jbwebinarjr. I welcome Dr. Jbwebinarjr at the digital platform of JBNSTS. And definitely this is a very good morning that we can connect Dr. Jbwebinarjr from Cornell University. And now the young scholars will be inspired by his work and total journey of his life. That is very encouraging to you, the young scholars. Dr. Banerjee perhaps is aware of JBNSTS and our enthusiasm of our young scholars who are all very brilliant students. And now in this pandemic situation, we cannot organize the physical workshop or physical seminars, etc. So during last 4 months, we are organizing this type of digital workshops. And definitely this is a privilege for us so that we can get such esteemed scientists like you at this platform. Dr. Banerjee started his career with honors in physics from Bardwan University. Then he completed his master's and PhD in Jadavpur University. And from there, he went abroad for postdoctoral fellowship. And you know that he went to several places. He had his journey at Vanderbilt University, Nashville. Before that, he was also in different scientific positions in India, like Dr. Reddy's laboratory and all these things. And after that, now, perhaps you know that Cornell University is a very one of the world famous university, and this is a platform for scientific research and innovation. So this is a very good opportune moment for you that you can get Dr. Banerjee, who has published several research papers, chapters, patents, etc. And he's the staff scientist now at Cornell University, and he has been awarded with different fellowships, different scholarships all over his journey. So I think today he was also awarded the Young Scientist Award, Young Scientist Travel Award, which are the very prestigious award from CSIR in India. So today we generally in different seminars and symposiums, we always discuss that science is such a platform where there is no barrier between physics, chemistry, biology, even our mathematical sciences. So today his topic is the X-ray crystallography and its application in different field of science. You will find that as in today's world, a protein crystal is important for us. So to know the protein structure, once upon a time, Mr. Peduch and Ken Drew, they invented the structure of hemoglobin and myoglobin crystal. That was a very important thing. Also from solid state chemistry, the crystal structure, the crystal interface, from organic synthesis, a crystal structure decipheration is revelation of the structure is also very important. So this is such a field which is important from physics, chemistry, biology, and even the structures of, even nowadays, for nanoscience and technology. So this is a very important one, and Dr. Jbwebinarjr will be discussing about this. After his lecture, you can always have a question answer session, and even sometimes if you cannot understand, যদি তোমাদের কোথাও অসুবিধা হয়, ডক্টর সুরজিৎ ব্যানার্জি আমাদের ওয়েস্ট বেঙ্গলেরই ছেলে, কাজেই তোমরা নিশ্চয়ই তাকে বাংলায়ও প্রশ্ন করতে পারো, উনি বাংলাতেও দরকার হলে বুঝিয়ে দেবেন। তোমরা যেরকম কমফোর্টেবল ফিল করো সেইভাবে তার সঙ্গে কথা বলো। আর ডক্টর ব্যানার্জি ইজ আ ভেরি ওয়ান্ডারফুল পারসন, আমি সরজিতের কাছে শুনেছি, কাজে তিনি আজকে তোমাদের সঙ্গে আমাদের সবার সঙ্গে থাকবেন এবং এরকম একজন ব্রিলিয়ান্ট সায়েন্টিস্ট আমরা পেয়েছি, এটা আমাদের খুবই একটা সৌভাগ্য। থ্যাংক ইউ ডক্টর ব্যানার্জি, প্লিজ ইউ ক্যান স্টার্ট।
থ্যাংক ইউ, থ্যাংকস আ লট ম্যাম। বেশ ভালো লাগলো এরকম ইন্ট্রোডাকশন, অনেকটা ইজি করে দেয়, রাইট, পাথওয়ে। সো if you are all comfortable with English ongoing, I can start. If you want me to continue in Bengali, just আমাকে যে কোনো সময় বলতে পারো, ওকে? সায়েন্টিফিক টার্মিনোলজিতে একটু প্রবলেম হয়, যেমন ডিফ্র্যাকশনকে যদি বাংলায় বলতে বলো, হয়তো এমন কিছু একটা বলবো যেটা হয়তো তুমিও বুঝবে না, রবীন্দ্রনাথ হয়তো বুঝবেন না। তো সেই জন্য ইংলিশেই বলি, তারপরে যখনই যেটা অসুবিধা হবে সেটা আমাকে পজ দিও। আর যেরকম বললেন ডক্টর ভট্টাচার্য যে লাস্টে কোয়েশ্চেন অ্যান্সার সেশন হবে, সেটা হলেই ভালো হয়। কিন্তু যদি তোমাদের কোনো কিছু দুর্মূল্য কোয়েশ্চেন আসে, হঠাৎ করে মনে হয় কোনো একটা পার্টিকুলার স্লাইডে যে এইখানে আমার এটা এখনই জানা দরকার, তা নাহলে আমি এর পরের স্টেপে প্রসিড করতে পারবো না বা কনসেন্ট্রেট করতে পারবো না, ফিল ফ্রি টু স্টপ মি, কোনো অসুবিধা নেই, ঠিক আছে? কিন্তু যা স্লাইড আমার কাছে আছে, আমার মনে হয় 1 ঘন্টাতে আমি উতরে যাব। আর তারপরে কিছুক্ষণ সময় তো নেবই আমরা একটু ডাইলিউট করার জন্য সাবজেক্টটাকে। লাস্ট স্লাইডে আমার ইমেল আইডিটা দেওয়া আছে, যদিও গুগল করে আমার নামটা কর্নেল দিলে পরেই প্রথম হিটটাই আসে আমি, এবং তাতে ইমেল আইডিটা এখন সর্বজন স্বীকৃত। তো তোমরা সেখান থেকেও গুগল করে আমাকে যে কোনো সময় অ্যাপ্রোচ করতে পারো। বাট যদি কোনো সিরিয়াস কোয়েশ্চেন থাকে, এরকম কোয়েশ্চেন করো না যে আপনার নাম কেন সুরজিৎ ব্যানার্জি, সেরকম উত্তর কিন্তু একটা মুশকিল। কিন্তু হ্যাঁ, মানে কোনো সিরিয়াস যদি কনসার্ন থাকে সাবজেক্টের ওয়াইজ, আমি খুবই গ্ল্যাড আমি যদি কোনোভাবে তোমাদের কোনোভাবে উপকৃত করতে পারি। আউট অফ 164 আমি অ্যাসিউম করছি 162 স্টুডেন্টস আছে, 161 আমাদের এই 3-4 জনকে ছাড়লে পরে বা 60খানা, তাদের মধ্যে যদি একজনও যদি at the end of 1 hour একটু মোটিভেটেড হয়, দ্যাট ইজ মাই গোল, ওকে? জাস্ট 1. So I am keeping my goal pretty low. I hope I will achieve. ওকে, তাহলে আমি প্রেজেন্টেশনের মোডে যাই।
আমরা অলরেডি 175 হয়ে গেছে।
175 হয়ে গেছে। ওকে, দেখেছেন কাউন্টিং আমি প্রবলেম করছি, তার মানে এখানে রাত যত হচ্ছে আমার তো মনে হয় সেরকম ভাবে আমিও জড়িয়ে পড়ছি। ওকে, কনফার্ম মি যে সবাই ঠিকঠাক দেখতে পাচ্ছে, অ্যাটলিস্ট ডক্টর কর আপনি যদি বলেন দেখতে পাচ্ছেন, রাইট? স্লাইড,
I can see.
okay, perfect. So here you go.
Yeah, fine.
Yeah, so welcome everyone and thanks for coming. Okay, as you already know that I'm the person today who is going to get you bored for an hour with very hardcore science. Now the best part of this talk is this will be a talk which will consist of several parts of science, okay? Several parts of science. So whatever you are studying or you have studied in your 12th standard, the basic science like physics, chemistry, maths, and biology. Maybe some of you have done stats and other thing as well. So if I think that these are the principal colors of science like physics, chemistry, and math, and biology, then this subject of crystallography will consist all of them, okay? And not only that, I will show you and I will prove to you that this subject has a tremendous potential. I'm not giving an advertisement to come to join this science after you are done with your research or done with your coursework, but I am enjoying my life. I have started my career with small molecule. You know, molecule can be small and large. Like large molecule, we usually call them protein, DNA. But small molecule means the organic, inorganic molecule, whatever you see. Just like for an example is glucose is a small molecule. Sodium chloride is small molecule. So let me start with a very positive hope, okay? Because this is a morning and especially Friday morning for you. You are all in very festive mood. Weekend deal, right? So here you go. So the very first slide, this is pretty hopeful for me because this subject has given to science a lot, and the science or the scientific community has given the scientist a lot. As you can see on the right hand side, the table shows from 1901 till 2012. If I can hide this one, I'm sorry. Okay, are you okay, right? This one is okay. Can one confirm me, please?
Yes,
okay,
yes,
good.
it's okay.
Thank you. So as you can see, this list is pretty big compared to the prize. So these are the people who got Nobel Prize in who is related to crystallography somehow. Okay, X-ray or crystallography. So I call it X-ray crystallography. So very first one was 1901, Röntgen, when he invented the X-ray, and after that you can go through the list and come to 2012, when Brian Kovilka and Lefkowitz got Nobel for the structure of a very famous drug target called G protein coupled receptor, GPCR. So the variation here is, the fun part is this. If you see, there are several subjects like physics, not several, like variation is here, like physics, chemistry, medicine as well. So there are 3 different subjects got the Nobel for the same work of X-ray crystallography. And because crystallography's application is various, I am going to show you this one in my next 40 minutes or so. So we are proud that one of our Indian origin got the ribosome structural Nobel in 2009, along with Tom Stites and Ada Yonath. And I'm lucky enough to work with Tom Stites and Brian Kovilka little bit of my career, which is a pretty enormous blessings for me, which crystallography has definitely honored in that sense. So here is what I was trying to say. This is a kind of a Venn diagram, kind of an overlap diagram. Don't go with the overlap value. Don't say that, okay, you have no overlap between mathematics and biology. This is just a kind of presentation that I have, okay? So this is showing you just all the subjects that come across in your path, right? You have used mathematics. You are using it pretty enormously. especially calculus and very classical mathematics. And physics is definitely the backbone of math. There is a humongous overlap between these two subjects. And you have physical chemistry, you have biophysics, which is biology and physics, and joined together biochemistry, which is biology and chemistry. Computation is everywhere. You can do a lot of simulation work, which is biology oriented. You can do mathematics, definitely comes as computation. Physics has enormous effort on the computation as well, and chemistry is definitely, if you see various aspects of inorganic chemistry and physical chemistry. So I think we are somewhere here. Okay, we are everywhere. That is one scary part. That means you have to learn all of the subject by taking it very seriously. So it is not like syllabus education. Okay, it is the education by heart. You have to learn it. Then only you can earn it. Okay. So in this talk, what you are going to expect is a flavor of all this basic science. I hope you will get the flavor. I'm not going to go in very details to bore you enough, because I can go and say a tremendous number of equations which are involved in our daily life, in my daily life. But those are done in the background, right? Computer does this all kind of jobs. So I'm not going to go in details for maths, but I will show you mainly my favorite part. My background is physics. Okay, so I came from here, and now I am working here. Application is biology. So all the instrumentations and whatever is there, I'm using from the physics knowledge. I am still learning the chemistry, and definitely doing a lot of computation using programming language, like maybe some of you are already started doing some programming coding like Python, C, C++. And then definitely mathematics is a blessing, because I have done a lot of work with physics. So forced to learn maths, and I love it. And definitely the subject I didn't like at all when I was at your age, my additional was biology. And I didn't know that I will end up here doing biology. Okay, so take it seriously, whatever you want to read. Do not give up on anything. So here I am. Currently, I'm sitting very close to this ring. This is the lab. Just to show you the dimension of this one, the periphery, the circumference, whatever you are seeing is almost 1 mile, which is 1.6 kilometer. Okay, so this is the circumference where the electron rotates, and it emits the photon, which is X-ray, which we use. And my lab is this particular triangle. We work in this zone, and my lab name is NECAT, which stands for Northeastern Collaborative Access Team, which run by Cornell. But I am located in Chicago, which is Argonne National Laboratory. So I'm affiliated to Cornell University and Argonne National Lab, working with all the physicists and mathematicians on a daily basis, and working for a very prestigious university called Cornell. And I work with Columbia, Cornell, Harvard, Sloan Kettering, MIT, Rockefeller, and Yale. Mainly all these things on a very daily basis on their required scientific projects, which most of them are application towards drug discovery, to find the medications for a basic disease, which is which we all are going through, right, on our daily life. So how the ring looks like? So here is the physics. Now we are entering the first subject, which is physics. So this is the ring. Ring is, like I told you, this is consists of the ring. The main ring is this one, which where the electron finally circulates. But first it bombarded here in the linear accelerator called LINAC. And the LINAC is actually the bombard electron, and then electron moves and in a bunch or packet-wise fashion. And then it goes to this particular ring. I don't know, my cursor is not working. Okay. The small ring called booster ring. And in this booster ring, the electron rotates for some time. And when it reaches the particular speed of very close to light speed of light, then we move this electron to the main ring called storage ring, because it stored the electron. That's why it's called storage ring. and then it. Excuse me.
Sir, we cannot see your cursor.
You cannot see my cursor.
No, sir, I cannot see.
Oh, okay. Okay. So
Yes, sir, I'm facing the same problem.
I'm sorry. So yeah, you don't have to complain each and everyone separately, but I got it. So looks like the cursor cannot be viewed like the other streaming device will share the cursor, but somehow this one is not. Okay, no problem. You will understand what I'm talking about. There are 4 different parts of this ring: LINAC, booster, storage, and beam lines. And we work in the beam lines, which is the application side. So this is what the ring looks like, and the ring has a very periodic manner of magnets. Okay, there are tons of magnets. Why I'm telling all these things are very close to physics, right? Because we have done a lot of magnetic field study, maybe electromagnetic as well. So you know how it works. So we take that very basic science knowledge and apply in this very crucial manner in this enormous instrumentations, which is 1 mile length, right? If you take as a linear path instead of circular. So so whenever this electron rotates, it goes through several magnets. Some of the magnets are small, tiny, and they keep the electron on track. Those called undulator or insertion device. And then you have some of the places had bending magnets, and those bending magnets are responsible to bend the electron, because you can assume this is a circle, right? And circle can be presented as a polygon, a many gone, right? So instead of 6, you can think of like 100 sides are there. If you draw a circle with 100 sides, that will become more or less a circular object. So this is the same thing like here. So those magnets are responsible to bend the electron to put them back in the circular path. And when it bends, it actually emits energy. Energy comes as a photon, and that's what we are seeing as X-ray, which is the black lines tangentially going out. And that's where the beam lines are. The magnet, just to give you a flavor, this one is taken last week, I think, yeah. These are the raw magnets. Small red and white are the linear magnets, and there is somewhere a black magnet, which is the bending magnet, which is not seen here, maybe almost at the end of the photo, which is not that very common. Only 34 bending magnets are there in this entire ring. And APS, this Advanced Photon Source, where I work in Argonne National Lab, we are trying to even boost the energy higher. Okay, so this is a very brilliant source. Brilliance in the sense, brilliance is the unit for brightness. Okay, so Department of Energy of USA is going for even higher brilliance. So we are going to put some magnets. So the basic thing is, whenever you are studying a magnetic field or electromagnetic field in your study, in your next career path, whatever the basic science you are learning from there, the application is exactly the same way. So maybe the best small equation, whatever you are using in your exam, is the same application over here as well. These are the 4 magnets, and between them there is a small hole, which is the very vacuum path for the electron. And as you can see, electron will move in a perpendicular way. You will have electric and magnetic field, and those are the source of all the energies emitting from the electron, from a moving electron. Okay, so this is like I'm saying again, this is very basic science, very true basic science. Okay, nothing fancy about it. Only fancy thing is how to control the electron in this particular path. Okay, always it should be confined, and it should not deflect, it should not get lost. So that is the magic here. That's what these people are doing. Maybe in your lifetime you will definitely see one synchrotron source in India as well. That was very close discussion. Maybe it is going to happen in Science Institute or in IISc Bangalore. I'm in touch with them. Maybe one day it will come out. So application of the synchrotron X-ray, high intense X-ray is enormous. Okay, so on the left hand side you can see this protein structure. Then you have material science. Application of material science is again like in your flight path, you have the flight upper outer core is the aluminium, that particular metal which was generated by looking at the X-ray vision of this particular material, which can survive very low temperature without frosting outside. And on the left side, you have the medicines. Then you have the imaging technique, which directly can image a brain, a particular organ, very high intense X-ray, not like which is we do in our X-ray machine in the hospital. That is pretty less intense. But this one can penetrate even higher. So it can see the density of the bone marrow as well. Okay, so the bone calcium deposition, how it is getting, like a very common disease called osteoporosis, which is a disorder of bone. So to see the density of the bones, you can use this high intense X-ray. Then you have this glass material amorphous studies as well, liquid crystalline. Geological survey, material metal content in the depth wise, especially geological era wise, you can define a location and the depth by the metal deposition and metal content of it. And metal means, I'm saying parts per million, it is very, very minute, but this X-ray can handle that. X-ray can pick it out. Then you have the battery technology, which is very application, various applications, but most applications nowadays is electric car, which is coming across slowly. I think the main emission problem or pollution will go away slowly in maybe a couple of years, maybe a couple of decades, who knows. But the only thing is, now we know how to drive with the battery, but we don't know how to smaller the battery size. Nowadays, the electric car has enormous size of the battery, and the lifelong longevity of the battery is also pretty low. So the efficiency need to go high, as well as the performance need to go high as well, and the price need to go down. That's the whole business policy. Then you have the solar panel, the solar energy, how to store the solar power. Definitely you have seen the growth by yourself sitting over there, that you are seeing in some of the street lights. You have the solar panel, which is going low by cost, and efficiency is higher and higher. Even a semi-cloudy day, you can restore the energy because of the blessings of X-ray. And then you have microchip. The phone you are using right now, the computer you are using, the price is going down and down and down, and the content is going up and up and up. Like you used to have 250 MB, now 250 GB, now 2.2 terabyte, right? So those things are the same price because of the X-ray. We know how the conductivity can be increased within a small and smaller pathway. That's why Apple is so expensive. So the question here is, have you seen any photons? The answer should be from your side. You should be nodding left and right, not south and north. That means you haven't seen. But I also saw when I moved to this country, this is the way to see the photons. The photons can be seen when you are using some kind of fluorescence screen or fluorescence crystal. This is a BGO crystal, which is a bismuth germinate crystal, which give you a view of the beam. So the left hand side, that's a raw beam. The beam is pretty wide. It is almost 500 micron on the left and right, the intense position, and the upper north and south, the up and down is depth is kind of 70 micron. And so this is the raw. And then what we do for our subject, my subject is protein crystallography, like Dr. Bhattacharya already mentioned about it. So protein crystallography need a smaller beam, okay, because of the divergence and many other aspects. I will touch upon a couple of the topics. So on the very right side, you are seeing a very small beam, which is 5 micron in size. And 5 micron will give you 10 to the power 10 photons per second. These numbers just to give you a flavor so that you are not going to sleep, okay? Just to give you kind of binding energy to the talks. But this has definitely some meanings. If you want to dig it out, please go ahead and Google it. Not now. Give me another 30 minutes, okay? So so these photons are actually responsible for the diffraction, what we are going to see now. But the smaller the beam, the more focused the beam is better for us. Why so? I will tell you. But like I was telling you, the magnet, whatever was coming across, like this one, is going to make the beam even 1 micron size. So now we have 5 micron, but it will become 1 micron in 2022, and even more strong. So 10 to the power 10 now, it should be 10 to the power 14. So it will be pretty strong beam, but strong is better for most of the applications, not macromolecule, not like protein crystallography. Protein crystallography, we are pretty happy, but smaller beam is better for us for sure. Now I'm going to hop on to my favorite area, which is protein crystallography. So what we do in my daily life, right? So this is how it looks like. On the very left side, you have a glass beaker with a plate, and the plate has a red dot, which is a protein solution. And in the blue liquid is a precipitant, which has a couple of components. One is pH buffer, one is precipitant, and another one is salt. And then you keep that protein solution on the top, hanging from it, so that it can seal. There is no leak of evaporation. And that whole environment between the blue liquid and the red dot is filled with very saturated vapor. And then slowly that red dot, whatever the protein is there, this protein molecule will come across and they will assemble among themselves and form a crystals, which is the slide, which is the position B. Those crystal looks very fancy, and then we take the crystal to this X-ray machine and shoot them with photons. Photon will hit the electron cloud of the atoms. If you can assume, you know the atomic structure, the nucleus, and then the electron cloud. It deflects from the electron cloud, get the information, and then go and hit the detector. The black dot on the position D is the detector image. It comes as dot, 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 which is very boring, but that's have all the information you need. And then after a couple of computation, like I was telling you, severe steps of mathematics, a high level of computing, we get the ribbon diagram, which is the protein structure. And why we need the protein structure? The macromolecule or the protein structure is very important. So here is a basic history or the background. So drug molecule is a small inorganic or organic molecule, like mostly metal organic kind of thing. So that organic molecule is excuse me, that metal organic or the organic molecule go and sits in certain position of a protein. Protein has several pockets, or one protein has one very active pocket. Why? Because protein is consist of various amino acids. Let me show you something which is don't know where I kept it. So these are the protein building blocks, right? So protein consists of various amino acids, and these amino acids has this distribution depending on the charge distribution of them. Okay, so the functional moieties, if you will. So you can see there some of them are acidic, some of them are basic, some of them are amide, aromatic, all kind of things, right? So depending on these variations, the pocket of the protein molecule are having different affinity. Okay, so you know, always everybody loves the minimum potential energy. Like we jump from a wall, we always hit the floor, right? So this is the minimum potential energy. So to hit the minimum potential energy for protein, you need to have a kind of handshake between the protein moiety, particular that particular pocket, with some kind of drug molecule. Drug molecule has again a different kind of environment. If the protein has a very acidic pocket, drug molecule should have a very basic pocket, so that it will neutralize, it will close the activation. Okay, so that protein moiety which is very active, now the drug molecule come and binds there. I will show you, do not worry about it. Then the whole event stops, and that's what happened. That is what is our goal as well. Okay. Okay, now let me go back to that particular slide where I was I was spending some time. Okay, so this is the crystal gallery, right? So these are a couple of the protein crystal example, just to give you a very charming idea. Really, the protein crystals look like this. How come they have very sharp edge, or some of them are very blunt, some of them have multi-crystals? This is depending on their growth. Okay, so some of the crystals has a very affinity to grow in one direction, very long crystals, because the protein molecule come and sit next to each other, have a tendency growing in one axis more than the other. So that's why it always become elongated. Ribosome, for example, it always comes in a very long fashion. But if you think lysozyme, if you Google lysozyme after this talk, you will see that is the most studied protein molecule. And lysozyme can grow a very diamond shape, which is one of the yellow diamond if you see in the middle of the screen. So just to give you an idea, this is how the protein looks like. Now, why we need a smaller beam? Because smaller beam will help you to find out a particular portion of a crystal which is coming as a cluster. So if you see at the very bottom panel, all of the crystals has deformations. Okay, so some of them are growing like leaves, some of them are growing like algae, some of them are growing like Christmas tree, or maybe a plate, stack of plates, something like that. So if you have very minute small beam, then you can hit only one portion, one very selective portion of the crystal, which is still single. So what I mean by single, so this is how the crystal forms. Like I was telling you, the formation of crystal, the molecule comes, so the unit cell is one of the terminology here I have used, which is very common in my world, but not very common to use. So unit cell is a very fictitious way. Okay, so this is an assumption. So assume there is a big symmetry like this. Okay, so this is one of the symmetry. So on the left hand side where I'm saying crystal, the truck has a pile of bricks, right? But each and every pile, if you see, they are very symmetrical, right? So each and every pile has several bricks in them, and then you have 6 of those, right? So think about only one of them at a time. That is the crystal, and each and every brick is the unit cell. If you think in that way, that is the crystal. That is the single crystal, we call it. And on the right hand side, you have a disaster. The truck broke or something happened and all the bricks are falling apart. This is amorphous because there is no symmetry between brick 1 to brick 2. Okay, they are not related. They are not depending on each other. So this is called amorphous. So there is a basic difference between amorphous and the crystalline. So same here, like I was telling you, this is first one is a mono.
Hello, sir.
Yes.
স্যার অ্যামরফাস প্রোটিনের অ্যামরফাস স্ট্রাকচারের ক্ষেত্রে আমি এক্স-রে দিয়ে কি করে তার স্ট্রাকচারটা অ্যানালিসিস করতে পারবো?
না করতে পারবো না। আমি অ্যামরফাস দিয়ে কোনো ক্রিস্টালাইনের অ্যামরফাস দিয়ে এক্সরে কোনো অ্যাপ্লিকেশন আমি বলছি না। আমি জাস্ট ডিফাইন করার চেষ্টা করছি যে ক্রিস্টালাইনটা হয় কি করে। ওকে, অ্যামরফাস এক্সরেতে কোনো কন্ট্রিবিউট করে না। ইউ আর রাইট। আমি এক্সরে অ্যাপ্লিকেশনে অ্যামরফাসটা আনছি না। আমি জাস্ট ট্রাই টু ডিফাইন ইউ যে ডিফারেন্স বিটুইন ক্রিস্টালাইন অ্যান্ড অ্যামরফাস অ্যাসেম্বলি। ডিড ইউ গেট ইট? ঠিক আছে?
ওকে স্যার, থ্যাঙ্কস। থ্যাংক ইউ স্যার।
শিওর, no problem. তুমি সঠিক কোশ্চেনই করেছো। জাস্ট কনফিউশন এড়ানোর জন্য আমি এগোচ্ছিলাম, জাস্ট টু শো ইউ যে ক্রিস্টাল কিভাবে ফর্ম করে। ওকে, অ্যান্ড পলিক্রিস্টালাইন যেটা বলার চেষ্টা করছি সেটা হচ্ছে যে লং রেঞ্জ সিমেট্রিজ আর ব্রোকেন নাও। ওকে, so what is long range symmetry? So long range symmetry, we can assume this is infinite. So all these molecules are assembled in particular ideal order. Okay, all are parallel to each other. Now if you think about monocrystalline and polycrystalline, the symmetry is broken, but still there is a symmetry in a short range. So that called polycrystalline, which we call powder crystal. So powder crystal is nothing but crystal. You take a crystal, you crush it, and that crush still have very minute small chunk of single crystal, and that is also very applicable to crystallography. So what is the application? So this is the application of powder diffraction. So powder diffraction, once again, it is a very short range order of crystalline object. So powder diffraction is just like a fingerprint of a chemical compound. When I was in Reddy's lab, I used to do this kind of work a lot. In pharmaceutical industry, when you are making a small molecule, which is a druggable kind of thing, then you usually end up with the organic molecule with various isoforms or chiralities right there. So those chiral centers are responsible for creating this particular image. So you can see this ABCD are almost same, but there are vast difference if you see those particular arrows peaks, right? So one of them is missing in other, one of them looks different in the other, like that. So these are the fingerprint, the true fingerprint which differentiates between the isomorphs of the same compound. So if you have a R versus a S, you can clearly see them separately, okay? Excuse me. So this is the very first application of crystallography, which is one-dimensional crystallography. So the information is not 3D. You are getting information as a one dimension. You can see this, the x-axis is 2 theta and y-axis is intensity. And from this one, you can only get the information how the molecules are stacking, what is the difference between the stacks. That's it. But you can find out structure as well from there. I have solved in my life only one structure. Very, very, very difficult to solve a powder structure from this kind of diffraction pattern. But what I did, I think, a small molecule with 50 non-hydrogen atom with a copper in the middle. So the copper was contributing more, and from that information we went forward, and there is a lot of calculation in that one, because you are going from one-dimensional information to create a three-dimensional structure. So you have to do a lot of deconvolution of the graph as well. So that is one of the application, powder diffraction, right? And the second application is this is one dimension. Second one is the two dimension, which is called electron microscopy. But that is not a true crystallography application, because that in that one we are not using photons, we are using electron beams, which is not happening in my lab. Okay, that is a different kind of technique. So I'm not adding that particular information here, but I'm just telling you this is one-dimensional crystallography or structural work, and that is two dimension. And the third dimension, that is the three-dimensional crystallography, is my zone, which is kind of this one, sodium chloride. So you can think of the sodiums are the red and blue are the chlorine, like they stack like this. You have read this one, right? Now think about this small, this very easy structure, and replace those all green, blue and red dots by a protein molecule like this, right? So now this protein molecule, which is just behaving like a sodium, full sodium, and they are stacked one after another and giving a structure like this, okay? So this is how the protein crystal forms. Protein molecule comes close to each other, and they have some kind of bond sharing, mostly hydrogen bond between them, between various side chains, which are the amino acids I told you, and then they form this stack, just like the militaries. Okay, now protein crystal and inorganic or organic small molecule crystals, the basic difference is protein crystal has a humongous amount of solvent, which is water. So 50% to 80%. Okay, just like our body. Our bodies consist of several proteins, so the protein and we do have several amount, like humongous amount of solvent content as well. But that is one way blessings, another one is a curse as well. Because of that thing, protein crystals never diffract high resolution. High resolution, by resolution I means it is not going to give you a detailed information. To get the detailed information, the protein molecule need to pack pretty tightly. Pack means they come close, close and close. So there is minimum gap between two molecules. But it is very rarely happen, especially when you have a humongous size of protein, and because protein always respirates, that means they move around. There is a dynamics between different moieties. And that's the beauty, because our body is mostly work very nicely at 37 degrees Celsius inside, and then you have a pH variation in the in your stomach. It is very acidic. Somewhere it is pH 7. Somewhere it is maybe a little bit of basic as well. So depending on the pH and depending on the temperature, all these things, the whole content varies. Okay, but now the question is, so a protein which is inside our body and a protein which is in a crystal, how they are related, because a protein in a crystal is nothing but a isolated single protein, and in our body they are interacting with various things, so their structure should be different. Now this is a God's grace, okay, ভগবানের দয়া বলতে পারো যে the protein in the lattice, in the crystals, they fold the same way, which is the same folding like in our body, because that depends on the sequence. Okay, so how the amino acids are sitting next to each other, because that actually defines whether it will be a helix, whether it will be a beta sheet, whether it will be a loop, and all the substructures. So the whole protein structure in a crystal and in our body, in vitro or in vivo, they are same. Due to that particular reason, like Dr. Bhattacharya mentioned, that there was a goal to solve some structure, hemoglobin, on those days. So then we realized that, okay, oh, this looks like almost everything is obeying the same law. The dynamics is definitely different. It will be much easier, much practical if we can see straight in our body by X-ray, injecting X-ray to see the structure. Maybe it is going to happen, who knows, 10 to 20 years. Technology is growing, as well as our viewpoint, our thinking power, our simulation, everything is growing as well. So maybe we are going to see that. But right now, that's not the way. We crystallize them, we take the protein, we crystallize, and then we go forward. So this is how we collect the data. So on the left-hand side, you have the crystal. This is a ongoing video, which is a real-time video. You can see the crystal is rotating as well as translating. And the cross here on the left photo, red cross here, is nothing but the beam. So it is hitting that particular crystal. On the right-hand side, in a different window, you have the diffraction. The dots are the diffractions. So this is a real-time collection. Why am I showing this? This is a collection of exactly 28 seconds. And if I'm right, this is not showing the time here. So exactly 10 years back, when I was joining this lab, the collection time of such a crystal, such a data set, was exactly 17 minutes. So it was 17 minutes in 2010. And it is now 28 seconds. Better quality data, much efficient, because of the technology, because of the physics. Now we know how the counting works, because this white dots on the right-hand side is nothing but you are counting the photons, which is coming on a detector. How to move the crystal, we have learned that. We have improved our robotic version. We have definitely improved our computation as well. So in 10 years, I have seen a growth which saves from 17 minutes to 28 seconds. Okay, so this is an humongous. If you think about the how much it has increased, this is humongous. Time is money, so yeah, definitely a lot of money. But the best part is, because of all this technology came across, collaborations has occurred, and we have seen the blessings of science. So this particular image is showing by physicist, chemist, computation, and definitely altogether crystallography, and the application, and the crystal came from the biologist, right? So here you go, in one slide, 5 subjects for you. Now this all started with a very basic equation, which you can correlate from your knowledge. This is so think about those black dots. The area of black dots are the lattice, like the molecules or the atoms or the protein molecules are sitting, and then incident X-ray is coming, which is the blue curve, because it is a wave particle duality, we know that. So this coming like that, and then getting reflected. Okay, Though we are saying reflection, but reflection is not the proper word. We call it diffraction, but let's assume this is a reflection, because then the reflection law can be applied, and then we can show you how this particular equation form n lambda is equal to 2d sine theta. You can, most of you are saying, okay, I'm done with this, because I can clearly see, right? D is the vertical distance between two layers. So you can, the gap between two layers, D spacing we call it. And then you can think of the path, the second wave, the wave below went more than the first wave, is nothing but d sine theta on the left hand side and d sine theta on the right hand side. So xy and xyz, right? So xy plus yz is the total path length. It actually moved extra compared to the first one. Now, if this path length is nothing but an integral multiplication of the lambda, the wavelength of the incident ray, then voila, then you have this equation, right? Which is nothing but d sine theta plus d sine theta is equal to n lambda, which is 2d sine theta is n lambda, which is pretty easy equation, right? It took several years to find out that particular equation by Bragg, William Bragg and William G. Bragg, father and son, both invented this one, and they got Nobel for this particular equation. So now you're thinking, okay, for this small equation, one can get Nobel? Oh my God, this is insane, right? But no, that time it was very thoughtful. Like you can think about E is equal to mc square. How easy is that, right? But it took several years for even Albert Einstein to think about E is equal to mc square, which you can memorize within a second, right? You know E is equal to mc square, but he didn't know that. So that doesn't make us smarter, right? But this equation was the backbone of crystallography. This is the equation which actually creates, solves everything. So blessing starts from 1912, okay? And then we have Fourier transform. Because in the microscope, in the first portion, you have the light, which is the visible light, suppose. Then you have a lens, and the lens always converge and not diverge, right? So here you converge or magnify the image, and then you can clearly see it, right? Which is the microscopic principle. Now for X-ray, the diffraction, like a reflection we are showing, oh, now the diffraction term we are using, is hitting the object and then going to somewhere, and then we want to magnify the image, right? Because it is coming from very tiny atomic distribution, right? Electron cloud. Now, there is no lens because X-ray cannot be converged by using a lens, right? Optical lens. So we invented detectors. Detectors are nothing but a counter. So it is, it actually counts in the entire face of the detector, several photons, and then it keep adding up. So we will get one information, which is nothing but how many photons did it count on a particular pixels, particular place, right? Which is the white dots that we saw in my previous video. So we invented the detector, not we. By we, I mean the scientific community. I am nothing. I have no idea. I just use it. So these are the two detectors up to date, till date. This is the best detector possible in the world. And we have it in our beamline, and this actually counts the photons pretty accurately and pretty efficiently. Like I'm saying, for this detector, we move from 17 minutes to 28 seconds. And then now we have to have the Fourier transform, right? So maybe some of you have heard this. A guy named last name Fourier has done this very ugly looking equation, but efficiency wise it is humongous. So you have done summation, integration, like various tough mathematical form. This is one of such mathematical form which looks for so from one space to another space, it actually translates. So think about this. So you have a film camera. Maybe some of you have used it. So a film camera, you see the object, which is a real space. You are seeing a tree, which is a real tree. Now you're snapping it. It comes through the lens, it get inverted and go to the film. It etches the film. Now when you develop the film, after developing, you get the real photo printed, which is again the real space. But meanwhile, what happened? Meanwhile, so suppose if you have seen one of your passport photo, negative of the passport photo, you have seen that your eyeballs are, or the black portion of the eye lenses are white, and the white part is the black, because that is inverted. That is the negative. That's why we'll call negative. So that is nothing but the Fourier transform, if you think about this way. So a real space to inverted space to real space again, which is the printed photo. So we are going from real space to real space. This is also the same case here. We started from a crystal, we got the real space. Now we are going to detector, which is the inverted space. So we are doing a Fourier transform. And then we are doing the reverse Fourier transform to take the charge density, how the charge is distributed. That information is needed. That's what we are looking for, because we cannot see the particular each and every atom in such a way, but we can see a cloud of it. Okay, so if we can do that, then we will get an idea where each and every atoms are there. Now, a protein molecule is not consist of only 17 or 18 or 30 non-hydrogen atom. It is a humongous structure, right, and very complex as well, because you are going, the X-ray is going through a cage of structure. In the cage, very left-hand side, you have one carbon, then you penetrate maybe 1700 of them, and then you go on the right. So you have the depth, you have the surface, you have all kind of distribution as well, and they slowly decay because of the X-ray has very high energy photons, so it actually kills, it actually break the amide bonds, the backbone of protein as well, so which call radiation damage. So this all keeping in mind, we have to be quick and fast and accurate, because we cannot lie. So whatever information we are getting from the crystal, we have to deconvolute that. So Fourier transform is the way. So this step is defining you one example of how important the mathematics is for our subject. Okay, so this is one of the example, like I'm saying Bragg equation or the Fourier transform. We have several such examples which are working in the back end of the experiments. No one knows, or most of the people ignores. They just wanted to have the result. But my request to you all, because you guys are just starting your journey, try to learn what is happening in the back end, what is happening behind the scene. Okay, because once you start learning that, you will get a much more grip into it, the subject, because then you will get the real pleasure of it. Otherwise, you will become an user, not a creator. So do some Fourier transform by hand, okay, in the pen and paper. You can do it. You can do it. I have done it in my PhD life. That is not easy, but there's fun doing it. Okay. So this Fourier transform, definitely this is the way to go. So like I was showing you the diffraction image in the video. This is the right hand side, the circle. The black dots here are the nothing but each and every spots which are defining a particular coordinates and particular intensity. So the coordinates will give us some idea about the phi, which is the phases on the right hand side of the slide, the bottom portion, and the FHKL is the amplitude. This amplitude is giving you is coming from the how intense the black dots are, and the phases is coming where it is located. So where it's located is the fun part to do it, which is called a phase problem in crystallography. If you Google it, phase problem in crystallography, it will give you enormous study to go through. That was a fun thing some people have done. So on the left hand side, the rho XYZ is the density map, which is called charge density, or the electron density, I'm sorry, is a real space phenomena. So we have to come in real space from the right hand side, which is the inverted space. So that is the Fourier transform is doing from right to left, left to right. Okay. Now, just an example. Okay, how far we are. Just let me know if I'm going so slow. Okay, I can move it faster. Dr. Kaur, I'm okay.
Okay, it's okay.
It's okay.
You're absolutely fine.
Thank you.
Absolutely.
So now, just to give you an example, enough of the boring. But this example, as you can see, I'm showing you in the blue some of the hydrogen bonds. So now I'm moving to chemistry. So physics, math, I've touched a little bit. Now the chemistry, little bit I'm touching, because chemistry, you guys know a lot more than me. So don't ask me any chemistry questions. You will be I will be ashamed. No, not really, but yeah, don't try me out. So this is a very basic example of A and T and G and C base pairing in our DNA. DNA is the base pairings. These bases are the basic building blocks of DNA. Thymine, adenine always pair together, cytosine and guanine. If it is not, suppose if a cytosine is pairing with adenine, then it will become a DNA fault, okay? Which happens. So when you go to Digha, for example, Puri, and you are sitting in the beach in a sunny day, due to the solar radiation through your skin, per seconds, there are some heavy number of damages in your DNA just by the solar radiation and by the ultraviolet, suppose. And but our system is smart enough, some of the machines like ribosome, smart enough to find out a defect in your DNA sequence and put the correct on the opposite side. Some of the time they fail to do that, and that's called anomaly, that's called problem, okay? That problem can be anything. And those problems like suppose a patch in your skin or a red eye or blood clot, something like that. So any anomaly can happen due to a small breakage, but that small, like by God's grace again, it get auto fixed. Now these are the base pair of well known, right? There are 2 hydrogen bond in the AT base pairing and 3 hydrogen bond in the CG base pairing. Now think about 1952. 1952, Rosalind Franklin, she has taken a step and she was trying to prove Watson-Crick's hypothesis. Watson and Crick mentioned just before that okay, there's a DNA is always come in double helix fashion. Okay, their prediction, their hypothesis, they were not proven yet. And this lady has moved forward, took a sample of the DNA and ran through the X-ray at that time. Okay, so she got this particular image. Instead of sharp small spots, she got this tricky X kind of symbol. And from there, she calculated the spacing between those black streaks. And as it is a inverted space, if you do that despacing calculation, 2D sin theta is equal to n lambda along with some of the Fourier transform, you can find out this base pairing is nothing but spacing between 2 DNA base pairs, okay? Because DNA base pairs are having a fixed gap between them. On the right hand side you have the stacking, so these are the base pairing. So you can see 0 is the center, and then she calculated 1 2 3 4 5, it went like that, and up to 10 base pairs she has calculated using this low resolution thing. So it was heavily challenging for them, for sure, but that was 1952. 2020, we are here, okay? I solved the structure, not 2010, I'm sorry, 2018. I solved the structure of a DNA, and this came out like this handy thing, right? Where you can see clearly a very nice CG base pairing. Now, if you remember, the C was like this, right? It has a CH3 on the left-hand side. Sorry, cytosine has no CH3 on it, like thymine has it. Now, this one has just 3 of the moieties on the right-hand side to pair up with guanine, right? But here we have one additional moiety. So this is a modified cytosine. This is a modified cytosine. It's called 5-HMC. It has some name. But look at that particular moiety of red dot. Reds are mostly oxygens, and blue are cyan, or the light blue are carbon. Dark blue are nitrogens, okay? So you can clearly see, or on the right hand side, the green are carbon, okay? So on the left hand side, on the CX9 molecule, it has one particular moiety which is standing upright, but the X-ray has clearly pointed out, okay, which way it is directed. Now we have such a high resolution, very high resolution, and clearly it depicts the absolute coordinate of it. On the bottom also, it actually moved on a little bit on the left side, and it clearly figured it out. So how we figured it out? Because of this particular Fourier transform, because of the absolute accuracy in calculating those particular black dots called diffraction. And from there, using some algorithm and high power computation, we are coming to this particular conclusion today to show you the particular hydrogen bonding in both of the base pairing on up and bottom, top and bottom. Both of them are left-hand side are modified cytosine, and right-hand side they are clearly guanine. They are waiting for the 3 base pairs, and the 3 base pairs are served on the left-hand side. So the hydrogen bonds are clearly showing off over here. By X-ray, we cannot see the hydrogen because hydrogen is small enough and it has no electron cloud. It has only 1 electron which move around and which cannot be located or pinpoint. But by another technique called neutron diffraction, which take information from the nucleus instead of electron, can be used to find out the location of hydrogen. But for that, that's a completely different subject. That's called neutron diffraction. If you are interested, you go ahead and Google it. We do have a very huge facility. Maybe one of you end up coming to Oak Ridge National Lab in Tennessee. They do a lot of neutron diffraction over there to find out the absolute coordinate of a proton called hydrogen. So this is a very very good news that we can locate each and every base pair pretty accurately. Now, this looks a little blurry to me, but bear with me. Now, this is one of the polymerase, DNA polymerase. So, okay, what is polymerase? Polymerase is a particular protein which actually extend the DNA, which actually make the DNA base pairing. Okay, so on the left-hand side, I'm sorry, you cannot see my cursor. That actually that stops me to explain everything pretty detailed. But just to show you, on the left-hand side, the red molecule, which is called AFB1 FAPI, is called aflatoxin FAPI. And if you are interested, write it down, aflatoxin, AFLATOXIN. Aflatoxin is the molecule which is a carcinogen, which causes cancer, mostly in liver. It is not very rare in hot and humid environment, a tropical environment like India, Africa. It actually starts from one particular...
Excuse me, sir.
I'm sorry, yeah.
Sir, I cannot see the diagram, sir.
You cannot see the slide?
Yes, sir.
Can you move? Not move. It's not move. You have not changed your name. Can you pin the Jbwebinarjr presentation icon on your participation list? There are 2 icons against Jbwebinarjr. You just pin where it is written Jbwebinarjr within bracket presentation. Then you can see his slides on your screen.
Sir.
Okay. Okay. Please carry on.
Thank you. So this aflatoxin molecule, like I was telling you, this is a molecule which actually comes from an epoxide. The chemistry lovers should know what is epoxide. A very active moiety of oxygen, doubly bonded with some other moieties. And this epoxide is actually comes from one particular fungi, and that attacks corn, okay, bhutta. And those corn feeded to chicken, those chicken get the disease of this particular modified DNA. If you see the AFB1 FAPI that I made in my lab by modifying the DNA, by moving a particular cytosine, guanine, and just replacing that by aflatoxin. Now you can see by the length of it, it actually occupies 2 base pair spacing. Okay, so this is what happened in our DNA when it gets ruptured. And when this aflatoxin get into our DNA, it actually stalls to continue the DNA base pairing happening. So you can see on the right hand side the DTTP, which is a thiamine moiety is coming from the right hand side to base pair. Now it actually skips the aflatoxin, one of the moiety, and then goes to the next one. So now the DNA, whatever is the making on the right hand side called primer, so the left hand side called template, the right hand side called primer. So the primer is not making properly, so it has a defect. So that's called DNA damage, and this DNA damage causes the cancer. And how do we know these things? Because of crystallography, because it slowly went to this. So the green ribbon, whatever you're seeing on all around, is the protein. It's called DNA polymerase. So someone solved the structure of DNA polymerase 10, 12 years back, and then someone crystallized the DNA polymerase with DNA, and then they solved the structure. Then they saw this, how it works. Now here you can clearly see the magic of crystallography. When I was preparing the crystal, it was a work in the year of 2007. Okay, so pretty. So if you search my name with aflatoxin, you will see this particular work, which was a long back at 2010, I think. It has the beauty is when I was making this sample, I was mixing 3 different liquids. One is protein, which is DNA polymerase, another one is template, another one is primer. So this 3 things in a certain proportion, you mix them, you make the solution. Now, by their own virtue, by their own potential, they bring this 3 together. So the DNA polymerase will bring the template, and then they bring the primer and start making the DNA duplex. Now it stops here, where it stops at the right hand side. Now I added the DTTP, which is another small molecule, a nucleotide, right? And that nucleotide was added to the solution. And the beauty is when we have the crystal of this particular reaction and we solve the structure, we clearly saw this thing, which is popping out from the right hand side, saying that, okay, now I want to base pair with adenine. Okay, I'm going to skip the aflatoxin, I'm going to the next one. So this is how the damage works, and we have captured this particular snapshot, because crystallography is nothing but a snapshot of a dynamic behavior, if you will. Because think about this, you have a group photo taken by someone from your class, you are on the very last day of your school, and everyone was assembled together. Then the cameraman or camera person said that, okay, jump. All in 1, 1, 2, and 3, then you all jumped. Some of you forgot to jump, someone you didn't hear third properly, jumped before, someone after. So this dynamic photo, which is within your album now, has a separate kind of behavior, right? But that's what protein is. So when we crystallize nothing but a snapshot. And that particular snapshot actually captured that particular reaction mechanism, which is tremendous, which is amazing if you think about it, right? In a solid phase, a liquid behavior, whatever was happening in our body, in a solid phase, we captured the same reaction, right? So this is a very crucial application when it happened several years back. And now the DNA technology, DNA polymerase, DNA mechanisms, everything has flourished a lot. And many drug targets have been used by the polymerase as well, saying that, okay, now we know how to figure it out, how to cure this particular disease, mostly the skin disease, and some of other features as well. Now, painkiller, right? In your daily life, you are taking almost many days. After playing cricket, hitting the ball in football, you are getting ibuprofen, right? Or acetaminophen. Now, the third character is called acetaminophen. Now, acetaminophen is very hard to pronounce. I don't think any one of you ever heard it, right? The name. Maybe you have heard aspirin, you have heard ibuprofen, but not the acetaminophen. But let me show you the next slide. The same structure on the right-hand side. You all have heard this, paracetamol, right? Paracetamol is nothing but acetaminophen. You can see the COCH3 moiety over there. COCH3 with the NH bound. So how we came up with this kind of drug, and how do you know that this thing is getting work done, right? So what happened to paracetamol? So you have you have pain or you have fever, you have taken paracetamol, and then after 15 minutes, or maybe some of you after 5 minutes, some of you after 30 minutes, depending on the body volume.
Sir,
And
excuse me.
Yes.
Sir, I was
Yes.
saying that shouldn't it be acetaminophenol because there is an OH group at the end?
No, the generic moiety said that fein. Okay, this is a because this doesn't come as a single, so there should be R on the bottom, but it came as a fein. Okay, so if you see the drug moieties, they come like that kind of name, a generic name. Okay.
Okay, sir. Thank you, sir.
So, but definitely the chemical structure says that it should be a phenol, right? But phenol cannot stay alone, okay, as a floating moiety. It should anchor to someone, and that anchor I'm going to show you in my next slide. So yeah, thanks for asking. Thanks for stopping by. Feel free, anyone, okay, anyone, just stop me or get the info done. When someone designed this kind of drug, so these are the drug molecule, right? These are the medicines. When they design it, they need to know the protein structure. And because protein structure consists of this whole thing, they need to know the charge distribution as well. So that charge distribution need to be nullified, like I was telling you, because it has a OH at the top and there is an amide over there as well. So it will definitely anchor to some of the affinity group, okay? And this is how it works. So when you solve a crystal structure of a protein sitting with a drug target, so this drug design is a trial and error basis, okay? So it says, it is in our world, it says that a drug takes almost 10 to 12 years, comes from your brain to your mouth. What does that mean? Brain means you're thinking, okay? So you are designing a drug, you are thinking, you are extrapolating, you are assuming. You are doing a meeting with the group, you are thinking about the target, all these things started on day one, and it takes 10 years to develop a drug, and someone is consuming it, someone is taking the drug in their mouth. So it takes 10 years. So it is not a joke, right? It is a humongous process. Why? Because first of all, you can find several moieties which are very similar, and they will bind the same pocket of protein, and they will be happily binding together, and then everything will be done. But the problem will be there might be toxicity, there might be some efficacy as well, and there might be side effects. So suppose you have targeted a particular thing which is a painkiller, and that painkiller is damaging your kidney, okay, because it has a side effect, because it is toxic in such a way, it emits a byproduct in our stomach, and after that, when it move forward, it actually goes and sediment in our kidney, which comes as a calcium silicate, and then it actually started ruining the kidney as well, nephron, right? So those things takes a lot of time. Like you have heard the phase 1 clinical trial, phase 2, phase 3. First it goes through the mouse model, then the rat or monkey sometime, and then human. Human also, it need to go through several human genome, right? Because now we have a different birth origin, so our gene has also different kind of assignments, right? So one drug which works in our tropical environment in India might not work in Iceland, Reykjavik, which is a very low temperature place, and people are a different having a different kind of gene construct, little bit of different orientation, so that might not work at all, or maybe not in that efficiency. So they have to find out a close call which will work everywhere. That's why you will see some of the drugs are moving around in India, but you are not seeing anywhere else, right? So that is the licensing attitude. So as a crystallographer, our goal is to find out a particular molecule which binds to the pocket heavily, looking at the hydrogen bond sharing. So whatever information we get from the crystal structure alone, from the protein alone, we get the idea. Okay, then the drug started designing by chemist or so, and then they make like almost 100,000, which is 1 lakh molecules, suppose, and of which 1 lakh molecule we cannot test all of the molecule by crystal structure. So then some other group comes and try to look into the moiety, which will make the favorable hydrogen bond. They jot down and they give us 20, maybe 100 molecule to test with. Then we take the 100 molecules, soak them in the protein solution, and crystallize them together and solve the structure to see how they binds. Now you will see that some of the drugs, some of the medicines you take as 500 mg, and some of them are only 20 mg, right? Because the binding affinities are different. And so less amount of drug you are taking is, that means it is binding more efficiently, right? Because one of the very known drug is who has a insomnia, kind of a sleeping disorder, they usually take melatonin. Melatonin, if you take 3 mg, which is good enough, but for paracetamol, maybe you have to take 500 mg because the targets are different. So melatonin is targeting a different kind of protein, and their goal is different. Just to put you sleep, that means not like put you death, right? Just sleep for a couple of hours. So that means, okay, you need to have a small dose. And but for paracetamol, it need to act quickly because the temperature is rising, and if the temperature is rising, heart is pumping a lot of blood throughout the body, and the lungs is also running heavily. So you need to find a balance. So you need to bring the temperature down as quick as possible. So that's all depends on all the goal, all the targets. This is the very basic example how the hydrogen bond shares. Like here you can see the red dots are the water molecules. Waters are very vital, like I told you. This is the solvent, right? And solvent content is very important to our protein. And this particular example I'm showing you has 2 water molecules mediated hydrogen bonds. So this drug molecule cannot bind to the protein directly because it is small enough. But as the protein has enough water molecule to bear with, to share with as well, it actually gives liberty the particular drug moiety to bind the water molecule. And definitely this drug molecule need to be more dose oriented. So maybe instead of 200 mg, you need to take 1000 mg because it is a dilute sample. It may bind or may not bind. But the efficiency you can see there, right? It is clearly showing off. And crystallography actually clearly shows us this true structure, because water molecules, that oxygen we can clearly see by X-ray, okay? Not the hydrogen, but clearly you can see, because you can see the distance 2.7, 2.8. This is the favorable distance of a hydrogen bonding between 2 non-hydrogen atoms. I'm sorry. Okay, I'm very close to the end, looks like. I'm so maybe I have used the word resolution. Resolution is the unit to find out a particular atom in this close proximity. So that's why I titled the slide resolution is the unit of confidence, because how confident you are to locate a particular atom more accurately, that's what resolution is all about. So you can see the resolution is going. So resolution is just like your rank, okay? In your class, if first boy is 1 and you are 72, that means you are not better than the first one, right? So sometimes lower number is better, not like money. So this is the same. This is a reciprocal relation. So lower the number is the higher the resolution. So 0.6 angstrom is much better than 5 angstrom, okay? You can see that. So 0.6 angstrom resolution is clearly showing you each and every atom individually, spherical way. This small sphere is showing you the probability of finding that particular atom at the center of the sphere, okay? That means it is pretty tight. Compared to the first one, 5 angstrom is showing, oh, that moiety can be anywhere. I can fit it in a different way. So there is no confidence on that one. Now, my last part of the talk is the famous topic now, right? For which you are at home today. This particular fellow is called coronavirus. We are working on it. And this is the famous picture on the left-hand side. You guys have seen this one in Jbwebinarjr Putrika as well. They haven't solved the structure, but they have taken it from somewhere else, right? So this particular red triangle is called spike protein. And COVID-19, the disease, the coronavirus, this called SARS-CoV-2, the particular virus. SARS-CoV-2 is very efficient because of this particular spike protein. The spike protein is the anchor which actually goes and sits on the wall, cell wall of our cell, human cell, and then it penetrates through the cell wall and it actually moves its chromosome into the protoplasm of our cell, cytoplasm of our cell. So it moves from A to B, okay, because of this particular anchor, particular spike protein is called S protein. Now someone has solved the structure in the month of March and February as well. So because in 2009 there was a coronavirus epidemic came out, which was SARS-CoV, not 2. This is SARS-CoV-2, and that thing didn't have this particular spike protein, so it was not that contagious. Okay, and for this particular spike protein, this is humongously more amplified version of the first version of SARS-CoV. And so what is the benefit of being crystallographer? So here you go, on the right hand side you have the crystal structure. Now we know how it works because we have seen this fellow more closely, especially a particular histidine and a cytosine, cysteine 145 and histidine 41. They are mainly responsible for this particular active pocket, which actually anchor to the cell and then translate the entire chromosome to our cell. Okay, so it ruptured the cell wall. It actually opened up the cell wall, make a hole, and then move the virus source to our cell, and then grow, amplify that particular one from there to there. That's why if someone attacked by this one and he or she has some problem in their respiratory system, that actually accelerates pretty quickly. That's why they goes to ventilator, and within a day or two they collapse because of this avalanche work by this particular virus. And what happened, it attacks, it goes to the respiratory system, and then in the respiratory system there is another protein which due to this malfunctioning, which starts gathering some fluid. So the whole spongy lungs will fill up with fluid, and it cannot go to squeeze mode again. So lungs usually go squeeze, go inflate, squeeze, inflate, squeeze, inflate, like that. But that squeezing will not be done because it is now soaked with water. It's just like the same. You take a sponge, you soak it in water, you pull it out, it is heavy and it is not respirating. It is full of liquid, right? So that's what happened to our lungs, and then only ventilator and God can save, because we don't have any drug or vaccination. So so this is the crucial particular species that we have today. But scientists are very close to find out a solution of it. Vaccine wise, we are much ahead. Looks like we are almost there. Maybe the very beginning of next year we will have it. And drug wise, we are not sure, because again the drug takes 10 years, like I said to you, but it is not going to be 10 years for sure. But it will take some time, because to show them the efficacy and toxicity and all other functions of drug. But because of the structure and because of the function, so we know when we design the drug. Now this is the pocket where the yellow molecule can sit. We know that. Excuse me, did anyone shouted?
Anybody is that is questioning?
No, I think it was misplaced.
Okay. Yeah. Sorry for that. Thank you. So then this drug design is ongoing in various labs. 72 different lab has already jumped into it. They are trying to find out a particular drug which will be very much efficient to bind this particular functions and at least hold it, not kill it, at least hold it. So that it is just same like acting for a cancer cancer molecule, cancer tumor, right? So cancer tumor, like if you think about someone is there is no cancer drug, right? But someone is going through a chemotherapy. Chemotherapy is nothing but a blind guess of a drug, so it is full of chemicals which have no idea what is going to work, but someone is consuming because that's the last hope they have. So they are taking that one. Maybe 1% will work and the 99% will do some wrong thing. So the chemo will definitely always come with several side effects. You will see, but the only hope is if we can kill the particular tumor cell. Right, the same way, maybe we are going to do the same thing on this fellow again, just to give a pause to the function so that it is not going to slip from the throat to the lungs as quick as possible. Just to hold it in the throat for some time, or maybe depath it to the acidic environment of the stomach, so that it will go, instead of trachea, instead of split to the lungs, it will go to the food channel. And in stomach, it is not going to do any work because this is known for the respiratory system. Okay. So one of the molecule, very confidential, but someone is going through it, already patented. So they have named it 13B, and they have clearly seen a very nice feature, very nice strong hydrogen bond with a picomolar concentration. And so how to design it? How do they come up with this particular moiety? They have done several several trial as well. Now you can see those green circles, they have changed, red circles, they have changed, the blue circles as well. And they have come up with the most efficient on the 13B molecule, which looks like that, which shows the maximum affinity on the binding wise. But again, it is a pause, it is not a cure. It is just like cancer, it is a prevention, not a cure, something like that. So this is where we are now, as of yesterday. But X-ray can do much better. X-ray can go for crystallography, can give us a clear picture of the entire engine called ribosome. This is a ribosome structure, 50S and 30S together, which the RNA composed of RNA. So this is a tRNA, a huge chain of it, and this comes in not in Dalton. You can think of this as a 3.5 megadalton protein. And this is the engine which actually looks into your template and try to synthesize the protein accurately. Protein is nothing but, again, a DNA sequence and folded in a different way. So if you think ATC, AGC, those three codons is called DNA codons, and those three composed one amino acid. Okay, and that's how the protein synthesized, and this fellow actually creates it. And in the year of 2009, those guys got Nobel, Venki Ramakrishnan, Ada Yonath, and Tom Stites. They have solved the structure way before that, and in 2001, after several trials. But they solved it because of a huge collaborative effort between physics, chemistry, mathematics, computation, biology, and various others as well, other than politicians. So this particular engine is, excuse me, is very effective, but because after the structure came out, many drugs actually target straight to the ribosomes. Not very efficient because it's a huge one. Because can we cure even in the one step backward when someone is creating a wrong protein, right? So instead of creating, because what cancer cell does is comes and dismangle the whole DNA and saying that, okay, now take my DNA template and create my protein, okay, instead of your protein. That's why it actually amplifies, and the whole search and cure mechanism by ribosome and by some other protein also mess up, and then we have the cancer cell. So this crystal structure was a humongous leap of jump in our field, in our medicinal chemistry or medicinal science, I should say. Another aspect of crystallography, which takes the crystallographic help to give us more and more answer, is called molecular dynamics simulation. Simulation means it is a completely computational work. but definitely they take the information from experiment, which is crystal structure. So they take a crystal structure and they try to predict what is going to happen. Like this simulation is also a very big path for drug
Sir,
design.
excuse me.
Yes.
Sir, is this the diagram of a cell membrane?
Yes, this is a membrane which AVC transporter is working. On the left hand side, the protein opens it up. In the middle, it actually absorbs it, and the right hand side, it actually translates. So that's how we have the sodium and potassium balance in your cell membrane, right?
Yes, sir.
You might have known this one. So yeah, this is how it works. But for this particular picture, I'm not having any other information than just to show you the molecular dynamics simulation, because I don't actively work in this field. If you are interested, you can write to me. I can give you more answer. But the simulation need power, not manpower, but computation power. And so you need to have a supercomputer. So instead of having a small computer in your lab, just one CPU, you can think of this one as a parallel CPU that we have in our facility called Mira. And this Mira can be borrowed by time-wise, computation time-wise, and we borrow for some kind of work. But for simulation, they can give you 1 day, which if you think about 10 years back, this kind of simulation was an assumption, not a positive assumption. It was a dream, but now it is possible. So because of the growth of science, because of the growth of humongous amount of science. But this particular computation facility was grown because of the microchip, and those microchips are modified in some extra facilities somewhere in the world. I really appreciate your time, all of you, and I think I am done. Feel free to write to me this particular email I'm talking about. This is my official email, is jbwebinarjr@anl.gov. But as I requested in my board letter, please, serious queries, please, okay? Serious queries. Serious queries means the question should be authentic and answerable, okay? Do not test me. Just try to ask the question from your own instinct, okay? Just to learn it. I don't know everything, but I can try to find out who knows something to send it to you. And I'm done.
It's a wonderful talk, Dr. Banerjee. Thank you very much. And, yeah, just a minute. Shashwat, we'll take your questions. Shorty, may I request you to take the stage now?
Yeah. So before that, we can take questions for them.
Sir, if you could please explain that Fourier transform part once more.
Nice one.
Okay. Yeah. So I can go to the slide, but I can tell you. So the Fourier transform has Fourier transform is nothing but transforming a particular algorithm just to have a definite answer handy, okay, so that you can easily use it. So in this particular example, I don't know whether you can see my slide anymore. Do you?
Yes, it's there, but yeah, you're scrolling it down.
Okay,
fine.
Good, perfect. So this particular thing, here we have okay, let me go to this one. So in this particular equation, you have one intensity, okay? Intensity is nothing but the photon counts, okay? So for this particular project, I'm talking about the Fourier transform, how we applied, okay? Fourier transform can be integrated as well. So this is a summation. And HKL are the coordinates called Miller indices in our crystallography world. But to you, just assume this as a coordinate, okay? And but this is variable, okay? So that's why it's called, that's why it is in parentheses. And then it is amplitude, that's why it has magnitude only. That's why you are seeing the bars. And on the right hand side, on the right portion, you have e to the power minus 2 pi I, and then the phase part, okay, the phi HKL. Now the phi HKL is something like this. If I go to the earlier equation, like suppose, yeah. So on this one, you have various portion, the photons goes and hit the detector, right? Now, depending on the angular variation of where it goes and hit, it actually gives us some clue about the phase. Okay, it's not easy. It's not straight theta. Straight theta is only in powder diffraction, but for single crystal diffraction, we have to do some more additional calculation. It's called Laue diffraction. It has Euler geometry. It has various functions. But today I thought that I am not going to go into very details. But if you need to know much more about it, you can read it out just by saying Fourier transform and crystallography. It will send you the link of the book Stout and Jensen. Stout, S-T-O-U-T. Stout and Jensen has this book, very nice book, which crystal clearly depicts the way it explains how Fourier transform is being used on this one. Okay, but just to find out this particular theta angle variation, that is the whole entire goal over here, right?
Sir.
Yes.
Sir, sir, you could explain that part once more, that from going to real space, that negative photography part.
Okay, yeah, that was that was just a gesture, an example of it. But yeah, this is how you do it. So suppose if you were coming to this country, right? So you are coming to this country with some cash. You are not bringing Indian rupees. You are going to one exchange place and you are converting the Indian rupees to dollar. And then you're bringing dollar. You are done with US trip. You are going back to India. You are going to once more the exchange place and converting that to Indian rupees, right? So because of these two places cannot talk in the same language, you have to use that particular conversion, right, in the currency. It is the same kind of example over here as well. So you are taking an equation because the detector will tell you only a place of the location of the pixel, like on this one, a particular equation. Suppose, okay, yeah, this particular portion, I'm seeing some dots over here, so I know that okay, this particular dot has this much of amplitude and it is located exactly this much distance from the center and at this angle, right? So this will give us some information, but that information is in the reciprocal space. That means it is only dot and angle, right? But you need to have much more information, which is the real space is the information is coming from the electron cloud, right? So the atomic environment of that particular atom. So you need to have that particular information. So we have to convert that to electron density. So that's called density map, which is the left hand side, rho xyz. Okay, so you have to convert that to rho xyz. And so you cannot use the FHKL, which is just the amplitude, but you need to have that particular conversion, and that's why we are using that back and forth by converting this two fellow to this one, and then we are getting a density map like this one over here, right? A density map, and then if you are not satisfied, you are going back to again, and you are calculating that FC, you are getting the FC. If you are done with the FC, you are just calculating the phi, which is the phase. You are coming back again, you are calculating the phase, you are getting the density map. So this is a very iterative cycling process, and slowly you are building the whole entire molecule. That's how we do the structure of a protein. For small molecule as well, the same way, same principle works. Because small molecule has only a couple of atoms, so this is much easier and much quicker method. But for protein, it is unfortunately not.
Means that the left hand side of the equation is the real space, rho of xyz.
Yeah, that's what I mentioned over here as well, right? This is the real space. Do you see that?
Yes, sir. Sir, HKL, you told Miller indices. What is that Miller indices?
Miller indices, okay. Then everyone go home. I have to sit till tomorrow 4 o'clock. this will take some time, gentlemen. Okay, whoever you are, you have to do some study and then get back to me. Okay, I can sit with you one-to-one, no problem. But this is a particular way of presenting a crystal lattice. So this is calculated from the spacing between two lattices, like I was showing in the Bragg equation. So this is d-spacing. So d-spacing, from there we calculate HKL, and this is a different lecture. This is unfortunately cannot be answered in a simple sentence and not that easy.
Okay, thank you, sir.
Sir, I have a question.
Shomodev, they are in which class now? You are
Sir, class 12.
class 12. So once you passing out from that, you can, Dr. Banerjee, he can be recommended for Eddington Volume 4, maybe.
Okay, yeah, sure.
Yeah.
Anything, like, anything can be, like, whatever is understandable, you can read. But definitely, if you have more questions, feel free to write to me. I will try to take some steps. But here is my request. Questions can come, no problem. But if you can wrap it up within 10 minutes, that would be great.
Sir, I have a question.
Yes, Angon, carry on.
Sir, what was the mainly use of the Charger's rule that we learned that the adenine and the thymine content of the DNA is same? What had its role in the crystallographic analysis? Did it play any role, or it was just a noted fact in the analysis?
কোন অ্যানালিসিসের কথা বলছো কোস্তা?
চার্জাফের যে রুলটা আমরা জানি যে অ্যাডেনিন এর থাইমিন কন্টেন্ট আর গুয়ানিন আর সাইটোসিন কন্টেন্ট যেটা সেম, সেটা দিস ইজ চার্জাস রুল। আই থিংক এটা কি জাস্ট এটা রোড ফ্যাক্ট, নাকি এটার কোনো ক্রিস্টালোগ্রাফিক অ্যানালিসিস আছে? ইট হ্যাজ আ ক্রিস্টালোগ্রাফিক প্রুফ?
না না না, হাইড্রোজেন বন্ডের প্রেফারেন্সের জন্য এটাই হচ্ছে হাইপোথিসিস বলো বা রুল বলো বা মেথড বলো। ওকে, এটা হয়ে আসছে বিকজ গুয়ানিন অ্যান্ড সাইটোসিন তিনটা হাইড্রোজেন বন্ড বের করতে পারে, অ্যান্ড হুইচ ইজ ফেভারেবল, অ্যান্ড অ্যাডিনিন অ্যান্ড থায়ামিন দুটো হাইড্রোজেন বন্ড নিতে পারে, হুইচ ইজ ফেভারেবল ফর দেম, অ্যান্ড দ্যাটস হাউ নেচার ডাজ। ওকে, ওটা কেউ একজন নেচার করেছে, ওইখানেই তোমাকে বলতে হয় যে গডস গ্রেস,
মানে
আমরা একজন ভাই না।
মানে সামহাউ এটা এমন ভাবে অ্যানালাইজ যে ইট হ্যাজ দ্য লিস্ট পটেনশিয়াল এনার্জি অফ দ্য সিস্টেম। ওর যদি আমরা ম্যাপটা নিই,
যদি আমরা কম্প্যাটিবিলিটি ফ্যাক্টর দেখো, যে কোনো বন্ড ফরমেশনে দুটো মলিকিউল যখন বা দুটো অ্যাটম যখন বন্ডিং হচ্ছে, তখন কম্প্যাটিবিলিটি ফ্যাক্টর এবং স্টেবিলিটি, এনার্জি স্টেবিলিটি, এই দুটো জিনিসকে ক্যালকুলেট করা যায়। তো তুমি যদি সেটা দেখো, দেখবে এর সাথে টি এই বন্ডিং হবে, সি এর সাথে জি এরই বন্ডিং হবে। আদার্স বন্ডিং গুলো করে তুমি দেখবে দে আর ইন হায়ার এনার্জি স্ট্রাকচার, সো ইট ইজ নট স্টেবল, সো it bonds like that way.
Thank you, sir.
Yeah.
So,
yes,
স্যার আপনি যে ওই যে পাউডার ডিফ্র্যাকশনের ওই ফিঙ্গারপ্রিন্টের ব্যাপারটা বললেন, ওইখানে ওই যে গ্রাফগুলোতে যে 2 থিটাটা কি আর ওই পিক্স গুলো হঠাৎ গুলো কেন আসছে?
ও আচ্ছা, 2 থিটা হচ্ছে অ্যাঙ্গেল। সো তুমি কি আমার ক্যামেরায় দেখতে পাচ্ছ?
ইয়েস ইয়েস,
ওকে, গুড। সো অ্যাসিউম করো এটাতে স্যাম্পল আছে, ঠিক আছে? এক্সরে ইনসিডেন্ট এক্সরেটা ফিক্সড, এর কোনো ডিরেকশনাল চেঞ্জ নেই। আমি এটার মধ্যে স্যাম্পলটা রেখেছি রিফ্লেকটিভ মোডে, অর্থাৎ একটা ছোট।
স্যার একটু ওই প্লেনটা তুলুন, মানে মোবাইলটা ওই যেখানে আপনি দেখাচ্ছেন।
ও আচ্ছা, আমি আসলে আমাকে দেখতে পাচ্ছি না, দ্যাট ইজ দ্য প্রবলেম, শুড সি মাইসেলফ। সো যদি এটা যদি প্লেন হয় স্যাম্পলের, আর এটা যদি ইনসিডেন্ট এক্সরে হয় হুইচ ইজ ফিক্সড, অ্যান্ড এইদিকে যদি ডিটেক্টর আসে বিকজ ইট ইজ রিফ্লেকটিভ জিওমেট্রি, এখানে গিয়ে কাউন্ট হচ্ছে, রাইট? এখন আমি যদি এটাকে থিটা ডিগ্রি ঘোরাই, তাহলে তুমি জানো রিফ্লেকশনের ল অনুযায়ী এটা 2 থিটা ঘুরে যায়, রাইট? গুড, হিয়ার উই গো। সো ওই যে এক্স অ্যাক্সিসে যে ভ্যারিয়েশনটা দেখছো সেটা হচ্ছে 2 থিটা, অ্যান্ড ওয়াই অ্যাক্সিসে যে ভ্যারিয়েশনটা দেখছো সেটা হচ্ছে তার পার্টিকুলার 2 থিটাতে ওই অ্যামপ্লিটিউডটা আমরা দেখতে পেয়েছি, এন্ড ওই অ্যামপ্লিটিউডটা আসে ডি স্পেসিং থেকে। ডি স্পেসিং হচ্ছে अगेन ল্যাটিসের যে ফিকটিসাস স্পেসিং আমরা বলছি যে someone want to answer, go ahead.
So you can continue, please.
Okay, yeah, so so particular that 2 theta variation is noted, and ওই 2 থিটার জন্য যে কাউন্টটা আমরা করছি ডিটেক্টরে সেটা ডি স্পেসিং হিসেবে আসে, এন্ড ডি স্পেসিং এ যে অ্যামপ্লিটিউডটা আসে সেটা अगेन আমরা যে সিঙ্গেল ক্রিস্টালে যে ব্ল্যাক ডট গুলো দেখলাম যে মোস্ট ইন্টেন্স টু স্মলার, দ্যাটস হোয়াই ইউ উইল সি ইন লো অ্যাঙ্গেল মানে হচ্ছে যেটা ইনসিডেন্ট এন্ড রিফ্লেক্টিভ অ্যাঙ্গেল অলমোস্ট সেম সেইখানে অ্যামপ্লিটিউডটা বেশি। যদি তুমি এটা দিয়ে লক্ষ্য করো, এদিকে লো অ্যাঙ্গেলে এটা সবসময় বেশি থাকে, এন্ড দেন হাই অ্যাঙ্গেলে এটা ধীরে ধীরে ডিসিপেট করে। ওকে, যে মানে খুব হাই অ্যাঙ্গেলে আর পাওয়াই যায় না। সো এইখান থেকে আমরা কি ইনফরমেশন পাই? অ্যাজ আই সেড, এটা হচ্ছে ওয়ান ডিমেনশনাল জিওমেট্রি। সো ওয়ান ডিমেনশনাল জিওমেট্রি থেকে আমরা মোস্টলি যে স্পেসিং যেটা পাই সেটা হচ্ছে এ বি সি আলফা বিটা গামা। That is the unit cell dimension. A, B, C are the 3 sides of that cell, and alpha, beta, gamma are the angles between the planes. So, which is sufficient to say that this is the particular compound I'm looking at. Okay, dhoro tumi S isomorph of some compound dekhcho on the D versus tumi B te seta dekhcho ota hocche R isomorph of the same compound. And you can see the first peak is disappeared, second peak is deflected, third peak is nowhere, and fourth peak has jumped up, right? So এগুলো হচ্ছে ক্লিয়ার সিগনেচার, এন্ড ফ্রম দিস পার্টিকুলার কুইক, এটা খুব তাড়াতাড়ি হয়, এন্ড এই কুইক এক্সাম্পল দিয়ে কুইক এক্সারসাইজটা করে আমরা টপ করে বলতে পারি ওকে ইউ আর ইন এ রং কম্পাউন্ড, আর তুমি ভুল এক্সপেরিমেন্ট করছো, আর মেবি you have a receiving mixture of R and S, both of them, so try to separate them out. যেমন যে আইবুপ্রোফেন মার্কেটে পাওয়া যায় সেই আইবুপ্রোফেনে আর আইসোমারটা হচ্ছে এফেক্টিভ, এস আইসোমারটা এফেক্টিভ নয় হিসাবে সবাই জানতো till 2011, and then our group has published a paper, আমরা একটা পেপার পাবলিশ করি, সেখানে শো করি যে এস আইসোমারটা টক্সিক নয়, মেবি এফেক্টিভ এ অনুযায়ী ওটা একটুখানি কম, বাট স্টিল এটা টক্সিক নয়। সো রেসিভিং মিক্সচার ক্যান বি এ ড্রাগ অ্যাজ ওয়েল। সো রেসিভিং মিক্সচার সেপারেট করতে হবে না, রেসিভিং মিক্সচার দিয়ে দাও, তাহলে তুমি ওটাকে ড্রাগ হিসেবে ইউজ করো, সো দ্যাট দ্য প্রাইস ক্যান গো ফ্রম 50 rupees to 5 rupees, বিকজ তোমার সেপারেশন করতে হচ্ছে না। সো কেমিস্ট্রিতে অনেক বেশি টাকা কম লাগছে, কেমিক্যাল ফ্যাক্টরিতে স্পেশালি এপিআই অ্যাক্টিভ ফার্মাসিউটিক্যাল ইনগ্রেডিয়েন্ট বানানোর জন্য। সো আর এন্ড এস ক্যান বি combined together, right?
Thank you, sir.
Good evening, sir. Sir Bornopriyo.
Okay, Bornopriyo.
Sir, if there ever were to be a drug for SARS-CoV-2, could the spike proteins on the coronavirus act as the target protein for the drug to act on?
No, drug ওকে টার্গেট করলে পরে যেটা করতে হবে, you have to kill that particular fellow. Okay, because before it start working you have to kill the spike protein. That can be one of the way to go, but drug always try to say that okay, I maybe দেখবে তুমি যখন antibiotic নাও, they say that you have to take it for a course for the antibiotic, right? So you have to take first day, second day, third day, 7th day. If you are going to give up on third day, antibiotic is not going to work, because this all work together. It has a timeline as well. So same thing, যদি স্পাইক প্রোটিনকে টার্গেট করে অ্যান্ড ড্রাগটা যদি ওর উপরে ইভলভ হয়, তাহলে যেটা হবে কিল এট ফার্স্ট সাইট, যদি মারা গেল, তা না হলে ওটা কিন্তু সুপ্ত থাকতে পারে, embedded থাকবে, and then it can come up again. So maybe it is not going to show you any symptom like asymptotic লোক যেরকম ঘুরে বেড়াচ্ছে, but it can come up any day, which will be disaster. So drug target সবসময় এরকম করে করা হয় যেন ওকে সমূলে মারা যায়।
Thank you so much, sir.
Sure.
Sir.
Yes, Simon.
Yes, sir.
স্যার আপনি ওই যখন প্রোটিন বিল্ডিং ব্লক দেখিয়েছিলেন যে স্লাইডটায়, ওখানে একটা ভ্যালু, প্রত্যেকটার এমডব্লিউ একটা ভ্যালু ছিল, ওই ভ্যালুটা কি বোঝাচ্ছে? এমডব্লিউ ভ্যালুটা?
আমি যে অ্যামাইনো অ্যাসিডের এই কথা বলেছিলাম,
হ্যাঁ হ্যাঁ হ্যাঁ।
ওটা কোনটা তুমি ডাব্লিউ বলছো? ওটা এমডব্লিউ মলিকুলার ওয়েট কো 75 ডালটন, 89 ডালটন। তুমি যোগ করতে পারো। তুমি দেখো ফার্স্ট এরটাতে একটা কার্বন, আরেকটা কার্বন, একটা নাইট্রোজেন আছে, আর এখানে 5টা হাইড্রোজেন আছে, 2টো অক্সিজেন আছে, অ্যাড আপ করো, তুমি ওইটাই পাবে। গ্লাইসিনের ওটা হচ্ছে মলিকুলার ওয়েট, রাইট?
Yes.
থ্যাংক ইউ ফর আস্কিং।
Next, anybody? Is there any other questions from anyone?
Sir, I have a question.
Shreyoshi first, then Arghudip.
Sir, somehow, yes, sir. Somehow, if there is any connection between the extracrystallographic result and the spectroscopic result to analyze a crystalline structure?
Car crystalline structure?
For a chemical moieties?
শুধু ময়েটির স্ট্রাকচার ফাইন্ড আউট করা, ক্রিস্টালাইন এ দিয়ে ক্রিস্টাল তো না হলে তো সেটা কোনো চান্স নেই, কিন্তু অন্যান্য মেথড দিয়ে, যেমন ধরো মাস স্পেকট্রোমেট্রি, রাইট? মাস স্পেকট্রোমেট্রি অর এনএমআর, নিউক্লিয়ার ম্যাগনেটিক রেজোন্যান্স স্পেকট্রা, এগুলো দিয়ে খুব কুইকলি একটা আইডিয়া পাওয়া যায় হোয়াট কাইন্ড অফ ময়েটিস আর দেয়ার। সো ইউজুয়ালি কেমিস্টরা কি করে, কুইকলি ওই পাথটা নেয়, অ্যান্ড দে নিড মাচ লেস স্যাম্পল দেন ক্রিস্টালোগ্রাফি। ক্রিস্টালোগ্রাফিতে আমরা হচ্ছি অনেকটা স্পয়েলড চাইল্ডের মতো, আমরা অনেকটা কিছু ডিমান্ড করি, অনেকটা চাই, টাইমটাও আমরা অনেকটা নিই, কারণ ক্রিস্টাল তৈরি করতে অনেক সময় লাগে। বাট মাস স্পেকট্রোমেট্রি, ইউ জাস্ট টেক the sample, dilute it by 100,000 fold, and then inject it in a mass spectrometry, and then clearly you can get a picture quickly, you can get a picture of it. But definitely NMR দিয়ে আরো ভালো করে দেখা যায়, যেমন তুমি ধরো CH3 versus CH2, you can clearly see the difference between those two peaks. তুমি যদি গুগল করো, very easy way to go. So yeah, crystallography is the last resort for that.
That is extracrystallography is more effective than spectroscopic result.
Absolutely.
হ্যাঁ, মানে আমি বলতে পারি যে at least একটা কথা, যেহেতু এক্সরে ওটা দেখছে and আমরা ওটাকে ডিকনভলিউট করে ইনফরমেশনটা তোমাদের কাছে দেখাচ্ছি, তার মানে ডেফিনেটলি এটা সত্য কথা, এটাতে কোনো অ্যাজাম্পশন নেই, রাইট? আমি এটা খুব প্রাউডলি বলি, ক্রিস্টালোগ্রাফি ইজ জাস্ট লাইক এক্সরে, ক্রিস্টালোগ্রাফি ইজ জাস্ট লাইক গড, ইউ হ্যাভ টু বিলিভ ইট, ইউ ক্যানট সি দ্যাট, রাইট? তুমি এক্সরে দেখতে পাও না, তুমি ক্রিস্টাল অনেক সময় দেখতে পাও না, বাট তোমার যদি বিলিভ থাকে, ইউ উইল সি দ্যাট। বাট মাস স্পেকট্রোমেট্রি ডেফিনেটলি, এগুলো সবাই নিজের নিজের জায়গাতে খুব স্ট্যাটিক এবং খুব রিজিড ফেনোমেনা, খুব বিলভেড সবার জন্য, এবং সবাই ইউজ করে। Definitely এগুলো সবই সচল মেথড। বাট to answer a particular question, suppose you want to see the hydrogen bond and you want to see the moiety, how it is interacting with the protein molecule, the NMR is going to tell you this particular moiety is talking to this particular moiety, maybe because of the movement of the peak. NMR এর peak আছে called HSQC, সো ওগুলো তুমি দেখতে পারো গুগল করে, HSQC বলে একটা ম্যাপ আছে, একটা পিক আছে, সেই পিকটা ডিফ্লেক্ট যদি করে, তার মানে ইট শোজ আপ দ্যাট ওকে ইট মুভস। বাট ক্রিস্টালোগ্রাফি উইল ক্লিয়ারলি পয়েন্ট আউট, অ্যান্ড ইভেন নিউট্রন ডিফ্র্যাকশন উইল clearly point out where the proton is, hydrogenটা কোথায় আছে, so even better. But neutron diffraction need a huge chunk of crystal. We are happy with 1 micron size crystal, but neutron will say that we need minimum 500 micron. So difference.
Okay, sir, if we format a new molecule, then how can we analyze the structure, which elements are there or not?
New molecule means completely ab initio, completely new.
Actually, somebody asked me it is realized.
তোমাকে অলরেডি আনসারটা দিয়ে দিয়েছেন ডক্টর ব্যানার্জি, মানে আমি জাস্ট ডক্টর ব্যানার্জি উইথ ইওর পারমিশন একটা জাস্ট অ্যাড করব সামনে, যে ওইখানে তুমি দেখবে যে তোমার কাছে নিউ মলিকিউল আছে, মলিকিউলে কি কি থাকতে পারে, তোমার যা যা এলিমেন্টস আছে ইন দ্য পিরিয়ডিক টেবিল তার বাইরে কিছু থাকতে পারবে না। সো তোমাকে যেটা ফাইন্ড আউট করতে হবে যে কি কি মলিকিউল কি কি ওখানে এলিমেন্টস গুলো রয়েছে সেটা। তো ফার্স্ট ইউ ক্যান গো বাই দ্য CHNSO অ্যানালাইজার বলে একটা যন্ত্র আছে, যেখানে কার্বন, হাইড্রোজেন, নাইট্রোজেন, অক্সিজেন এই সমস্ত গুলো এখন ফসফরাস হয়, সেগুলো অ্যানালাইজ করলে তুমি জানলে যে এগুলো আছে কি নেই, কারণ মোস্ট অফ দ্য টাইম এগুলো দিয়েই সমস্ত অর্গানিক মলিকিউলস গুলো তৈরি হয়। যদি সেটা হয়ে গেল, যদি না পারো দেন ইউ গো টু দ্য মাস স্পেকট্রোমেট্রি। মাস স্পেকট্রোমেট্রিতে তোমাকে বলে দেবে যে কোন কোন এলিমেন্ট গুলো আছে এবং তার রেশিও কি আছে, কি মাস তার আছে বললে, এরপরে তুমি মোটামুটি টেন্টেটিভ স্ট্রাকচারটা পেলে, নাও ইউ ক্যান গো ফর দ্য আদার স্পেকট্রোস্কোপিক মেথডস এন্ড তারপরে ফাইনালি যদি স্ট্রাকচার জানতে চাও, তুমি যেই মুহূর্তে আদার স্পেকট্রোস্কোপিক মেথডস পেয়ে গেলে, নাও ইউ ক্যান গো ফর দ্য সিনথেসিস অফ দ্যাট মলিকিউল। সিঙ্গেল ক্রিস্টাল যদি করতে পারো, ভেরি গুড, দেন ইউ ক্যান গো টু ডক্টর ব্যানার্জি এন্ড হি উইল গিভ ইউ দ্য ক্রিস্টালোগ্রাফি। তো এইভাবে ইনিশিয়ালি অ্যাব ইনিশিও থেকে তুমি একটা পার্টিকুলার জায়গায় রিচ করতে পারো।
Okay, sure. Thank you, sir.
Thank you. Yeah.
Welcome.
So I think
Next.
I think we're done.
I think
Anyone
we
else?
can stop.
অর্ঘদীপ আছে, অর্ঘদীপ তোমার সাউন্ডটা কেটে যাচ্ছে একটু, হ্যাঁ বলো, রিপিট করো।
আমার মনে হয় যে ডক্টর ব্যানার্জি এবারে ঘুম পাচ্ছে, অনেক রাত।
But what will happen if you use gamma ray or UV ray for crystallography?
Nothing will happen. Nothing will happen মানে কিছুই হবে না, কারণ X-ray and crystallography is the word that we use, right? Gamma ray will not take the information whatever you're looking for because of the electronic structure of each and every atoms, right? If you look into gamma ray or beta ray or any other ray other than Satyajit ray, you will definitely see that the structural informations are not going to get there, right? So the gamma ray is not the way to go. X-ray, photon is needed. Photon is needed. That's where the energy conversion comes from. And I'm very sad to say that আমি তোমাদের বলছি যে okay, I'm kind of done for the day. 1:38 AM সকাল হয়ে গেছে, আবার সকাল উঠে আমার একটা মিটিং ফিটিং আছে, কারণ আমার শুক্র এখনো হয়নি, আমার শুক্রবার শুরু হয়েছে সবে, ফলে কাল আজকের দিনে আমার আবার কাজ আছে। সো থ্যাংকস অল ফর কামিং। খুব ভালো লাগলো তোমাদের সবার সাথে কথা বলে, হয়তোবা 1-to-1 কথা বলতে পারলে আরো ভালো লাগতো যদি আমি লোকেশনে থাকতাম। And thanks for inviting me to all of you, ডক্টর ভট্টাচার্য, ডক্টর কর এন্ড ডক্টর মান্না, যাকে আমি সরজিৎ বলেছি। সো সবাই খুব ভালো থাকবেন, and আপনার যদি কিছু বলা থাকে কনক্লুশন, প্লিজ গো অ্যাহেড।
থ্যাংক ইউ।
Thank you very much. Thank you very much. Now already he's feeling sleepy আর ওর তারপর কাল সকালে মিটিং আছে। আমি স্টুডেন্টদের সবার জন্য বলছি, তোমরা বুঝতে পারছো তো আমাদের সঙ্গে টাইম গ্যাপটা অনেক বেশি যেহেতু রয়েছে, ওর এখন রাত্রি 1:40। তো কাজে আর আমাদের ওর উপর অত্যাচার করা উচিত না। আমরা আবার ভবিষ্যতে কোনো সময় সুরজিৎকে, ডক্টর ব্যানার্জিকে আমরা আবার ইনভাইট কিন্তু এই যে এক্সাইটমেন্টটা হলো, ছাত্ররা ক্রিস্টালোগ্রাফি নিয়ে এত কিছু ভাবতে শিখলো, এটাই আমাদের একটা বিরাট পাওয়া। তার জন্য আমাদের ডক্টর ব্যানার্জিকে অনেক ধন্যবাদ।
থ্যাংক ইউ। ওকে,
আর এই অন টাইমে বিব্রত করার জন্য দুঃখিত।
না পারফেক্টলি ফাইন, কোনো অসুবিধা নেই। এটা আমি গ্ল্যাড যে আমি এটা করতে পারি। আমরা এখন এইভাবেই হয়তো আরো বেশি কমিউনিকেট করব, কিন্তু সেটা খুব এফিশিয়েন্ট হয়েছে, একটা পজিটিভ পার্ট অফ দ্য ভাইরাস, রাইট? যে তোমাদের সবাইকে দেখতে পেলাম, which is nice.
অনেক কিছু শিখিয়ে দিয়েছে ভাই।
হ্যাঁ, সবচেয়ে স্মল পার্টিকেল, সেটাই হচ্ছে সবচেয়ে মজার জিনিস, রাইট? ওকে, ঠিক আছে, হ্যাঁ, সবাইকে হ্যাভ এ গুড ডে।